Ever stop and wonder how the software we use every day gets so, well, complicated? I mean, from the apps on your phone to these huge, massive systems that run companies, how do they get built without just collapsing under their own weight? The answer, it turns out, is this really powerful idea, a sort of blueprint for programming called object-oriented programming, or OOP. So let's dive in and really demystify how this whole thing works.
At its heart, OOP was invented to solve one single, massive problem that programmers have always faced: complexity. As a program gets bigger and bigger, adding new features can turn into a total nightmare. You change one thing over here, and suddenly a bunch of unexpected bugs pop up somewhere completely different. So the big question was, how do you build something massive and still keep it from turning into a mess?
To solve this, programmers needed a huge shift in how they thought about code. The old way, what we call the process-oriented model, saw a program as just a list of steps. The code was the boss, and it just acted on data. But object-oriented programming completely flipped that on its head. It organizes everything around the data itself. You create these things called objects, where the data actually controls who gets to access the code. Now, that might sound like a small change, but trust me, it changes everything.
So, the secret weapon that makes this new way of thinking possible is a technique that, believe it or not, we humans use all the time without even realizing it. It's called abstraction, and it's basically our natural superpower for dealing with complex stuff.
Abstraction is really just the art of ignoring the details. It lets us focus on what something does without getting lost in how it does it. You do this 1,000 times a day. Every time you use your phone, a microwave, a car, you're interacting with a simple interface, not the thousands of little parts whirring away inside.
Yeah, this quote just nails it, right? You don't need to be a mechanical engineer to go to the grocery store. You just think of the car as a single thing, an object with a clear purpose. It drives. That right there is the essence of abstraction, and it's the first huge key to understanding OOP. Okay, so this powerful idea of abstraction is held up by three main principles. They're like the pillars that form the foundation of object-oriented programming: encapsulation, inheritance, and polymorphism. Let's break these down one by one. First up, encapsulation. This is the idea of bundling your data and the code that works on that data into one single self-contained unit we call an object. And here's the really important part. This protects the data from being accidentally messed up by some other part of the program. Thinking of it as a protective wrapper is the perfect mental image. It shields all the internal, messy complexity of an object from the outside world. All you get to see is a simple, clean interface to interact with. A car's automatic transmission is a fantastic real-world example of this. It's an incredibly complex system, right? But you only interact with it using one simple thing: the gear shift. You can't accidentally mess up the gears just by turning on the radio. That's encapsulation in action, a simple interface controlling a complex, protected system. All right, our second pillar is inheritance. This is all about how we create relationships between different objects. It lets a new object take on the properties and behaviors of an object that already exists. It's all about not reinventing the wheel, about reusing what's already there. You see these kinds of hierarchies everywhere in the real world. Think about it. A dog is a type of mammal, and a mammal is a type of animal. So when we're programming a dog object, it doesn't need to redefine breathes air or has a heart. It just inherits those traits from its parent classes, mammal and animal. It only needs to define the stuff that makes it uniquely a dog. Now, here's the real payoff. Because of inheritance, when you want to add a new kind of object, you don't have to start from scratch. This prevents a tiny change from creating this massive, unpredictable ripple effect across the whole program. It lets software grow in a much more controlled, manageable, linear way. And that brings us to our third and final pillar, polymorphism. It's a bit of a mouthful, but the name literally means many forms. And it's really a feature that allows one single interface to be used for a whole bunch of different actions. It's all about flexibility. It really just boils down to this one simple phrase: one interface, multiple methods. You have one standard way to ask for something to be done, but how it gets done completely depends on the specific object you're talking to. Let's go back to our dog again. The interface is its sense of smell, its nose. But the action that follows depends entirely on the data it receives. If it smells a cat, that triggers one response: barking and chasing. If it smells food, that triggers a completely different one: salivating and running to the bowl. See? Same interface, the nose, but multiple different outcomes. That's polymorphism. So there you have it. Encapsulation, inheritance, and polymorphism. But the real magic, the true power, happens when they all work together. So let's go back to our car analogy one last time and see how these three pillars combine to build a system that's complex, but still totally manageable. First up, inheritance. You can hop into a bus, a sedan, or a minivan, and you basically already know how to drive it, right? Why? Because they all inherit the basic properties of a vehicle. They've all got a steering wheel, an accelerator, and brakes. You're using what you already know about the parent class. Next up, encapsulation. Think about the pedals. They're your super simple interface. When you press the brake pedal, you don't have to know if you've got disc brakes or drum brakes or how the whole hydraulic system works. All of that insane complexity is encapsulated. It's hidden behind that simple pedal. And finally, polymorphism. When you press the accelerator, the car goes. That single interface, that one action, works whether you have a little four-cylinder engine, a big V8, or even a silent electric motor. The same exact action, pushing the pedal, controls all these different implementations. One interface, many forms. So you see, these aren't just some abstract academic theories. These three pillars working together in harmony, that's what allows developers to build the robust, scalable, and maintainable software that powers our entire modern world. It really is the blueprint. And that's the whole point, right? As this quote puts it, OOP lets us take what could be a chaotic mess of different parts and bring them all together to form a single cohesive whole. It allows us to manage complexity, to build for the future, and ultimately, to create software that actually works. So the next time you use an app or really interact with any complex system, take a second. Look for these principles. Look for those simple interfaces that are hiding a ton of complexity. Look for the common traits that are inherited across different things. And look for those single actions that can produce many different results. Once you know the blueprint, you'll start to see it everywhere.